So in this video we're going to do a short review of the concept of formula mass, sometimes referred to as molecular mass, and the mole concept. And as you know, the mole is a chemist's counting unit. So when a chemist is talking about a mole of a substance, it's kind of similar to a baker talking about a loaf of bread or a dozen donuts or something like that. It's a counting unit that we use in chemistry that's appropriate for the number of particles that we'll be discussing. So earlier we talked about the relative atomic mass scale, which assigns units of atomic mass units to every kind of atom. Now what we recognize is that these are weighted averages, but any particle, whether it be an atom, an ion, a molecule, or even a macroscopic particle, can be assigned a relative atomic mass in AMU units. And how we calculated this scale was we we just began with a definition, and we said that the carbon-12 atom that has 12 particles in its nucleus, 6 of those will be neutrons and 6 will be protons, has a mass of exactly 12 AMU. And then any other object can have a mass calculated in AMU as either a fraction or a multiple of this amount. Now, of course, atomic mass units are very, very small. They're intended to give a whole number for objects that are of the masses of atoms. And one atomic mass unit has a mass of about 1.67 by 10 to the minus 24 grams. We can define the formula mass of a compound as such. It's just the sum of the atomic masses of all of the atoms represented in the chemical formula of a substance. Now, it's important to recognize that when we write the chemical formula of a substance for a molecular compound, we never divide through the formula by the lowest common multiple, because that would give us the wrong formula for one molecule. So that's something to keep in mind. So when you calculate the formula mass, sometimes they'll refer to this as the molecular mass to remind you of that for covalent compounds, don't simplify your formulas. So to calculate one of these masses, all you do is add together the masses of all of the atoms that are present in the formula. So for this guy, we've got 2 times the mass of a carbon atom plus 4 times the mass of a hydrogen atom. Just use the periodic table that's provided to you, which in this case is going to be the one that is in ALEX. And so you want to be, just using the one that is appropriate for whatever you're doing. Sometimes you're doing a test, there'll be a periodic table attached to the test. Most of the periodic tables have the masses either expressed to 3 or 2 decimal places. So just use the one that you're given. Now, for an ionic compound, when we write the formula mass, it's important to recognize that the formula represents the smallest repeating unit, what we call the formula unit. And this will always be the smallest ratio of atom types. So we're never going to see Ba2S2, we'll always see BAS, and it's the simplest ratio of the atom types that we're going to be calculating the mass of. There aren't any molecules in an ionic compound. Ionic compounds exist as crystalline materials where we have an approximately infinitely repeating array of positive and negative ions. But the formula mass is calculated exactly the same way as for a molecule. We just sum the masses of the atoms that are in the formula. Okay, now these formula masses, whether they be for ionic compounds or molecular compounds, are going to be given in AMU, and they're never going to be less than the smallest possible molecule, which is a hydrogen molecule to AMU. So they're always going to be greater than 2, but then really where they can top out is unlimited. Very large molecules like proteins and DNA molecules, they have masses of hundreds of thousands of AMU. Okay, so AMUs are not very practical. They're really, really, really tiny, right? 10 to the minus 20, of the order of 10 to the minus 24 grams. We don't have balances that can measure that small. And apart from anything else, it's not like I'm going to be in the chemistry lab and be like, hey David, can you pass me like 10 carbon atoms? That's not going to happen. I'm not going to be weighing out things on the AMU scale, and I'm not going to be counting atoms and molecules one at a time. We need something more practical. So practical units of mass to be working in are things that are around about from 1 milligram, 10 to the minus 3 grams, up to perhaps maybe like 100 grams. They would be reasonable amounts of things, maybe hundreds of grams up to about a kilogram. So to kind of have more practical units for mass that we can use to count how many atoms and molecules that we're dealing with, we developed the concept of the mole. Just like bakers don't sell, individual slices of bread, they sell loaves of bread because that's what's sensible, right? So we have moles rather than individuals, atoms and molecules, because that's what's sensible. So what is a mole? Well, a mole is pretty simple. It's the number of carbon-12 atoms in 12 grams. So why did we choose this number instead of, say, the dozen of 12? Well, we chose this number because it really makes a lot of sense. Whatever the mass of one thing in AMU is, so 1 in AMU is the same as 1 mole in grams. So remember we said that 1 carbon-12 atom weighs 12 AMU, 1 mole of carbon-12 atoms weighs 12 grams, and that applies for any object. So if we go back to our molecule here, a mole of these molecules weighs 28.0454 grams, and one of them weighs 28.054 AMU. So it's really convenient. So how many are there in a mole? Well, obviously it's a lot more than 12 in a dozen. It turns out that in 1 mole of something, there are 6.022 by 10 to the 23 particles. And that number is referred to as Avogadro's number because Avogadro did a lot of work on counting the number of particles that are present in samples of matter. We give it a special symbol. It's an uppercase N, and then that's followed by a subscript uppercase A. And so this is the value that we're going to use out to 4 significant figures. So in one mole of particles, there are 6.022 by 10 to the 3 particles. This is most commonly used as a conversion factor. 6.022 by 10 to the 23 particles in 1 mole. Or the other way that we might use it is as the inverse. It means exactly the same. 1 mole contains 6.022 by 10 to the 23 particles. Now, what are our particles that we're interested in chemistry? They are normally either atoms, ions, molecules, and later on in chemistry 163 we'll see this, and even in 161 sometimes electrons, because electrons are very important in chemistry. But that's typically what our particle is. It's either an atom, an ion, a molecule, or an electron. Of course, you could apply the concept of a mole to anything. So Avogadro's number serves as a conversion factor to convert between the number of moles of a substance and the number of particles in that sample. So let's answer this question. Like I said, it can be applied to anything. It doesn't have to be atoms, ions, molecules, or electrons. We're going to answer how many moles of donuts are there in a 24 box of donuts. So obviously not very many, because 1 mole is 6.022 by 10 to the 23 donuts. Our object or particle in this case is our donut. So, we're not going to get many moles, right? So I'm going to use moles as a conversion factor. So I've got 24 donuts, and then I need a conversion factor that's got donuts on the bottom and has moles on the top, right? And so I know that 1 mole is the same as 6.022 by 10 to the 23 donuts. And sure enough, when I do that math, just as predicted, I get not very many moles of donuts, right? Okay, so this is how we're going to set things up. We are going to use conversion factors, we're going to label our units, and then we're going to cancel our units. And when people don't do this, because our problems are so very complex that we're going to be dealing with in general chemistry, they tend to get things horribly wrong. So the sooner that you get used to writing out problems using what we call dimensional analysis, which basically just means including your units and cancelling them, the better off everybody's going to be, and the happier I'll be, and the happier you'll be, and the more likely you are to get these problems correct. So Avogadro's number serves as the conversion factor between our number of particles, sometimes referred to as our number of objects, and the number of moles of those particles or objects. And so how we do that is when we're going from particles to moles, we multiply by 1 on Avogadro's number, and when we're going from moles back to particles, we multiply by Avogadro's number. We're going to use this as a conversion factor. When I'm going to moles, this here, how I'm going to write it, 1 mole is Avogadro's number of particles. Just like that, you see. And then over here, we've got Avogadro's number of particles, which is going to be Na particles in 1 mole. So, and then we know what Na is, right? 6.022 by 10 to the 23. Okay, so that's our first conversion factor. We're going to learn about 3 different conversion factors in general chemistry that relate to the amounts of substances. So, why is the mole useful? Well, I hinted at this before. As atoms have fixed masses, a mole of a pure substance will also have a fixed mass. And the cool thing about the mole of something is that the mass of one thing in AMU is exactly the same as the mass of a mole of that thing in grams. So we know by definition that one carbon-12 atom has a mass of 12 AMU, so therefore a mole of carbon-12 atoms will have a mass of 12 grams. One sodium atom has a mass of 22.99 AMU. An Avogadro's, or number of sodium atoms, or a mole of sodium atoms has a mass of 22.99 grams, and so forth. And we can also apply this to molecules. So one H2O molecule has a mass of 18.02 AMU. One mole of H2O molecules has a mass, you guessed it, 18.02 grams. So it's really cool, right? It works really, really well. So 1 mole of an atom or a molecule weighs an equivalent number of grams as the mass of 1 atom in AMU. This is referred to as the molar mass of a substance. So the molar mass of carbon-12 is 12 grams for every 1 mole, which we could also write as another conversion factor. We get 1 mole for every 12 grams. So we're going to be using the molar mass of substances as a conversion factor. What are we going to be converting between? Grams and moles. So we can apply the concept of the molar mass to compounds. So we said barium sulfide before. We said it has a formula mass of 169.39 AMU. Guess what? A mole of barium sulfide would weigh 169.39 grams. Or another way that we might say this, because it's complicated saying 1 mole of something weighs, we say the molar mass of barium sulfide is 169.39 grams. Often molar mass is indicated by an uppercase M or by a cursive uppercase M. You'll see later on that we use uppercase M to indicate other things, but remember molar mass is always going to have units of grams per mole. So if there's any confusion as to what that symbol is referring to, you'll know that it's a molar mass because it always has units of grams per mole. So 1 mole of a molecular compound weighs an equivalent number of grams as the mass of one molecule in AMU. So all we have to do to get the molar mass of stuff is just grab the masses of the atoms that are present in our molecule from the periodic table and then sum them together in the correct proportion. So for water, we need 2 hydrogen atoms. Each has a mass of 1.01 AMU, and then we need one oxygen atom has a mass of about 16 AMU. We add those things together, the mass of one water molecule, 18.02 AMU. So what's the molar mass of water? 18.02 grams per mole. Now you guys know that there are a lot of online calculators, so it's always well worth checking one of those guys. I just like have one bookmarked, put my formula in, hit enter, and it calculates the molar mass for me of whatever I'm interested in. So the molar mass, as I said, is often given the symbol uppercase M, and it can function as a conversion factor between the mass in grams, which we normally indicate with a lowercase m, and the number of moles of a substance, which you'll remember from the ideal gas law chapter, we indicate with the symbol N. So in particular, the number of moles is the mass in grams over the molar mass, and you can reorganize accordingly. So you can calculate the number of moles of something very, very quickly. It's grams over moles per gram, and away you go. So if you're a little, the simplest way is to always make sure you use dimensional analysis here. So it says how many moles are there in 2.54 grams of water. We know that the conversion factor between grams and moles is the molar mass. So the first thing I'm going to do is calculate the molar mass. So I've got 2 hydrogen atoms and 1 oxygen atom, 18.02 grams per mole. So then away I go, 2.54 grams multiplied by 1 mole per 18.02 grams. Grams cancels out, leaves me with moles. All right. Now I know it's going to be less than 1 mole because I need 18 grams to get a mole, and I've only got 2.54, so it makes sense that it's less than 1 mole. When you're doing a bunch of these, and you're feeling much more confident that you know you've got it, people will skip the dimensional analysis and they'll just calculate number of moles is the mass in grams over the molar mass and do these very quickly. Okay, so here's another one. How many moles are there in 3.54 grams of calcium chloride? So I know that to convert between grams and moles, I've got to use the molar mass. So the first thing I'm going to do is calculate the molar mass of calcium chloride. So calcium has a molar mass of 40.08, and then I've got to take into account that I have 2 chlorines. Don't forget that. So I get my molar mass of calcium chloride. Now my number of moles, it's just my grams divided by my molar mass, or my grams multiplied by 1 on the molar mass. I know I've got it right because my grams will cancel out. Now, a whole mole weighs 110 grams or 111 grams, and so 3.54 grams is going to be way less than a whole mole, and so I got a number there that is less than 1, so I feel pretty confident about this. Plus, I've also got, my dimensional analysis to help me keep my thoughts straight. So, if you do all of the right stuff, you should be able to detect errors very easily. If you kind of check for logic at the end, 3.54 is going to be way less than a whole mole. This number is less than 1, so that's great. And then, I've got my dimensional analysis there. Every unit other than moles cancels out, so I also know I've got it correct there. Odds are I've got this correct. Okay, so now we've defined a second conversion factor that helps us understand how the mass and the number of particles are related to one another. So to interchange between the number of particles, or sometimes referred to as the number of objects, and moles, we're going to use Avogadro's number. And then to move between the number of moles and the mass in grams of a substance, we're going to use the molar mass. So I like to sketch out this little diagram and just kind of refer to it as I'm doing these conversions. You can see that it is not possible to move from mass all the way to particles in one go. There's no single conversion factor that does that. We have to do it stepwise. Okay, so you're going to require 2 conversion factors to move between either mass and particles or particles and mass. You've got to go through moles to do that. The other thing that's worth noticing about this little diagram here is you can see that whenever we're moving towards moles, our conversion factor always has a 1 on the top line. So that can kind of help us, all right? So we always have 1 on the top line of our conversion factor when we're moving towards moles, and we always have a number other than 1 on the top line of our conversion factor when we're moving away from moles. So little hints, if you can keep those in the back of your mind, that'll reduce the errors that you're making. Okay, so this one, we want to go from moles into grams. It says, what is the mass of 3.20 moles of hydrogen peroxide? So the first thing to recognize is that this is converting grams and moles, so we need a molar mass. So I've got 2 hydrogens plus 2 oxygens, and so there's my molar mass. So now, pretty simple, 3.20 moles is what I'm given, and I got to multiply it by something that has moles on the bottom, and then I want to get into grams, and so that's it, grams per mole, isn't it? All right, so 34.016 grams for every 1 mole. Remember, whenever I'm moving away from moles, my conversion factor has something other than 1 on the top line. So this looks good, moles cancels out, boom. Unless I enter it into the calculator wrong, I've probably got it right. Every mole is about 34 grams. I've got more than 3 moles, so I should have a number that's bigger than 100, right? Because 3 times 34 is going to give me like 103, right? So 3.2 times 34, there we go. It's 109. I'm feeling pretty good. Okay, little doubt that I got that wrong. Significant figures here. This had 3 sig figs. This had 5 sig figs. So my answer has 3 significant figures. All right. This one's a little bit more complicated, and it introduces another conversion factor. Remember, I said that we're going to have 3 conversion factors in this section. It says how many hydrogen atoms are there in half a gram of water. So I know I want to go through to number of particles here, right? So, and I'm given mass. So I know that the first thing I got to do is turn it into moles. Okay. So I know that to do a mass to moles conversion, I need the molar mass. So I go ahead and I calculate my molar mass of my water, and then I use that to convert my grams into moles of water. So to get my moles of water, 0.5 grams of water times by 1 on the molar mass, and grams cancels. So I've got a lot less than a mole of water, which is good because I know a mole of water weighs 18 grams and I've only got half a gram. Okay, so here's where I have to get fancy. What I have to recognize is that for every mole of water, there are 2 moles of hydrogen atoms. And how I'm understanding that is because there's a 2 in the formula there, right? For every mole of people, there would be 10 moles of fingers. For every mole of people, there would be 2 moles of eyes. For every mole of, penguins, there would be 2 moles of wings, right? 2 moles of flippers. So that's kind of how it works, isn't it? If you had a mole of cars, there would be 4 moles of wheels, right? So in this case, we're talking about a mole of water water molecules. So there's going to be 2 moles of hydrogen atoms, 1 mole of oxygen atoms for every 1 mole of water molecules. So to get my moles of hydrogen atoms, I have to take into account that I get 2 moles of hydrogen atoms for every 1 mole of water molecules, and I knew from the previous part of the problem that I had 0.0278 moles of water molecules. So I have to multiply it by 2, right? So now that's how many moles of hydrogen atoms I've got, and I can now go on and turn that into particles using Avogadro's number, because Avogadro's number converts between particles and moles, right? Or moles and particles, whatever way you want to go. So to get the number of hydrogen atoms, I have to recognize that I get 6.022 by 10 to the 23 hydrogen atoms for every 1 mole of hydrogen. And then I multiply that by my moles of hydrogen, and sure enough, what have I got? My number of hydrogen atoms. And it's a really big number. And that makes sense because there's going to be lots of hydrogen atoms in half a gram of water molecules. Remember that it's like 1 atom is about 10 to the minus 24 grams. So it's going to be lots and lots of atoms in half a gram of molecules. All right. So that concludes this little review of the concept of formula mass, also referred to as molecular mass for covalent compounds, and a bit of a review of the mole concept, and in particular how to move between number of particles, number of moles, and grams of a substance.